We have already defined capacitance as the charge stored per volt placed across the plates of the capacitor. The actual value of the capacitance will depend upon the construction of the capacitor. It will depend on the cross-sectional area of the plates of the capacitor, A. It will depend on the permittivity of free space, which is a constant, and also the relative permittivity of the substance placed between the plates of the capacitor. And finally, D, the distance, the separation that is between the plates of the capacitor. We can perhaps make sense of that equation if we consider a simple capacitor charging circuit. Here we have a battery which charges up this capacitor through the fixed resistance. As the capacitor charges, electrons will flow off the negative terminal of the power supply onto the right-hand plate of the capacitor, and electrons are pulled off the left-hand plate of the capacitor and flow off towards the positive terminal, leaving this plate with a positive charge. As the charge on the capacitor builds up, the current in the circuit will decrease. What is happening is the PD across the capacitor is increasing as it stores more charge, and the PD across the fixed resistance is decreasing. Less volts through the fixed resistance, well, less current then is going to flow. Eventually, of course, once our capacitor is fully charged, no more current will flow. The PD across the capacitor has reached the same value as the EMF of the battery. We now have no volts across the fixed resistance, and hence no more current is flowing. What's really happening now is the electric push, really pushing electrons away from the negative terminal, is balancing out the electric push from the power supply, trying to push the electrons in the other direction, and we've essentially reached a standstill. No more current is going to flow. Clearly, if we were to increase the cross-sectional area of the plates of the capacitor, we will be spreading this charge here, the negative charge on the right-hand plate, the positive charge on the left-hand plate. If with a larger area and we spread that charge over a larger area, what that would mean is we would actually be able to store more charge on this capacitor for the same potential difference before then a current stopped flowing. Equally, we can perhaps understand that the distance, the separation between these plates here would also be important. What's stopping the capacitor gaining further charge is the electric field that's essentially pushing electrons away from this plate of the capacitor. It's balancing out the electric field from the power supply, pushing the electrons around onto that plate, and kind of two effects are cancelling each other out. But if we think about it, the positively charged plate is also going to exert its own electric field, pulling electrons onto this plate of the capacitor here. So really, the closer these plates are together, the more the electric field from the positive plate will cancel out the electric field from the negative plate, and therefore the easier that will make it to get more electrons onto this plate. Equally, if we increase D, we push the plates further apart, we move this positive plate further away, its electric field is not going to cancel out the electric field of the negative plate anywhere near as much. And that means we're not going to be able to actually get as many electrons onto this plate before the current drops to zero. So there we are. If we increase D, move the plates further apart, we're going to reduce the capacitance. We're not going to be able to get as much charge onto our capacitor. So there we are. Okay, if we want to get as much charge onto our capacitor as possible, what do we want? We want the cross-sectional area of the plates to be as large as possible, and we also want the separation of the plates to be as small as possible. Now the final effect is going to be this relative permittivity, which is affected by the material that we place here between the plates of our capacitor. Now the material that's between the plates of the capacitor is actually an insulating material that we call a dielectric. Now it's important that the material is an insulator so that we don't simply discharge the capacitor by allowing a charge to flow between the plates of the capacitor. The insulating material, however, will contain polar molecules, and we can see that here. These polar molecules, basically, one side of the molecule has a partial positive charge and the other side has got a partial negative charge. Now it is an insulator, so these molecules can't move through the material, they can't carry a charge from one plate of the capacitor to another, but they can rotate. Now here, in an unpolarized dielectric, these dipoles of the molecules of the insulator will all be arranged at random directions. So overall their dipoles will cancel out. There's no overall polarity here. But as soon as we start to charge our capacitor, one plate becomes positively charged and the other plate becomes negatively charged, what will happen is that these dipoles of the dielectric will start to line up. Now, if you notice here, look at this diagram here, notice the negative charges here of the polar molecules is pointing obviously towards the positive plate. Now, the result of that is that the electric field of the dielectric is actually in the opposite direction to the electric field between the plates of the capacitor, due to the charge on the plates of the capacitor. So what will happen is basically the electric field of the dielectric will partially cancel out the electric field being produced by the charge on the plates of the capacitor. And what that will do basically is it will allow more charge to flow onto the capacitor before the current drops to zero, in which situation the electric field of the capacitor basically is cancelling out the electric field of the battery and that no more current is flowing. So what we have here is a demonstration capacitor, parallel plate capacitor. Now let's just take a moment to understand exactly what apparatus we have here. So on the left we've got a high voltage power supply, and you may just be able to see that the negative terminal of that high voltage power supply is connected to the plate on the left. Now both plates of the capacitor then are connected across this needle electroscope on the right. Now the idea basically is if there is a voltage across the plates of the capacitor, one plate's positive, the other plate is negative, what that will do is it will cause the needle of the electroscope to stand out. Basically at the moment the needle of the electroscope is connected to the plate of the capacitor on the right, which we're going to charge in a minute positively. And what that will do is it will cause the metal stem and the needle of the electroscope to both become positively charged, and that will repel the needle away from the stem of the electroscope. And the size of the voltage, basically the amount of positive charge, size of the voltage that's really on that capacitor, will depend on how far that needle of the electroscope actually stands out from the metal stem. So what we will do is to move the plates of the capacitor closer together. We'll reduce the distance between them as much as we can so they're almost touching. And then what we'll do is turn on the high voltage power supply, and we will momentarily charge the capacitor by connecting the flying lead to the positive terminal of the power supply, charging the capacitor, and you can see the needle of the electroscope has stood out because we now have a voltage across our capacitor. We've turned off the power supply, we've disconnected the power supply now completely from the capacitor so that no further charge can flow onto or off our capacitor, and we will then move the plates further apart. What's going to happen? Well, you can clearly see that the needle of the electroscope has stood out from the stem much further. Now the reason for that, by moving the plates further apart, we have reduced the capacitance of our capacitor. Increased D, we reduce C, but because no charge can flow on or off the capacitor, we've disconnected it from the power supply. Q has got to be constant. If we've reduced C, then the voltage across the capacitor must rise, and that there is basically being measured by the needle electroscope, and it's indicating that higher voltage by standing out further from the metal stem. Now of course what we can do now is move the plates back closer together, and we should see the needle electroscope start to move down back. You can see it moving back down a little bit because now of course we've increased the capacitance again. By increasing the capacitance, that's reduced the voltage here. And again, going back the other way, move them further apart again, and obviously the capacitance is reduced, and if we're keeping the charge constant, the voltage must increase. Now in the comments at the bottom I've put a link to another video produced by the Massachusetts Institute of Technology using slightly more advanced equipment. It's probably a better demonstration here than we've got here. And they look at the effect not only of changing the separation of the plates, but also inserting different dielectrics, carrying out the experiment again, but this time keeping the battery connected. All these things. Have a look at their video, see if you can explain what's happening.